We want to have a look at an acid and base pH calculation questions. Right, this one is gonna be interesting. Right, now when an acid, we have an acid reacting with a base. When an acid reacts with a base and they have an equal amount, they have the amount are not equal. Now what will happen is that what will happen is that one of them will be in excess and the other one will be a limiting reagent. So we know that whenever a base, let's say you have got 2 moles of an acid here, and then you have got about 3 moles, 5 moles of a base. What will happen is this: when we react these two, what will happen is that this mole and this mole will cancel. This mole and this mole here will cancel. That is to say, they neutralize each other. And then now what will happen is that you will be left with this 3 number of moles. We can see that now the base was more than enough, and because the base was more than enough, now these 3 number of moles of the base will give us the pH, because they will be the ones that are left in the container when a base reacts with an acid. Right, so this one cancel with that one, this one cancel with that one, because an acid and a base, they fight each other until one of them wins if they don't have equal amounts. Okay, yes, right. So then the 3 number of moles will determine the pH of the solution. So which means would be the pH of a base. The base will determine the pH in this case. So, but let's see what happens there as a model. Let's see the model of what really happens. Of hydrochloric acid, then NaOH, sodium hydroxide. Then now you take this, now you mix them. Now these two will now react with each other, and when they react with each other, the hydrochloric acid will be, so these two, they will neutralize each other. These two will neutralize each other, and then now you will be left with excess number of moles of NaOH. And now this NaOH will determine the pH of the solution. Today we have solution of hydrochloric acid. Right, we're going to look at another acid and base questions. I'm going to give about more than 10 examples here in the in this okay session. Right, so we're saying now, when we have an acid that reacts with a base, okay, we have an acid that reacts with a base. Now what is it that's happening when an acid reacts with a base and they don't have equal amounts? Okay, if they don't have equal amounts, this is what is happening. If I have 2 particles or 2 moles for an acid, these are the particles for our acid, right? Then we mix it with a what? With a base. For example, NaOH, right? 1, 2, 3, 4, 5. Then the NaOH has got this number of particles. If you mix these two, this is an acid and this is a base. Okay, now what is it that is going to happen? What will happen is that these particles and this particle will will fight each other, will neutralize each other. Okay, and then this particle here and this particle, they will fight each other. So all of the acid will be consumed, right? And then two acids will consume two particles of a base. Then you'll be left with three particles. For what? For a base. You'll be left with three particles. You'll be left with three moles of a these three moles here. They are what we call excess number of moles. They are what we call excess number of moles. Initially, they were how many? There were 5. So initial number of moles were 5 of them for the base, right? And then for the acid, initially the number of moles were actually the number of moles were 2 of them. And because the base is more than enough, what will happen now is that it will remain. It will not react all of it. Not all particles or all moles of the base will react in this case, right? So two particles from the acid, they will neutralize with two particles from the base. Then the acid will get finished. So in this case, the acid is called what we call a limiting reagent, whereas the base now, in this case, it will become the excess reagent. It will be in excess, and those number of moles that are in excess are 3 number of moles. Yet initially there were how many? 5 number of moles. Then now the ones that reacted, how many are they? So I just say okay, then ones that are reacted, I can see how many they are. Right, they are actually 2 of them. 2 of them actually reacted. 2 of them reacted. 2 moles reacted. Those 2 moles reacted with these 2 moles of the acid, and then we remain now with what? We remain with 3 number of moles for the base. Okay, then these 3 number of moles that are remaining, remember now we only have the base that is remaining inside the beaker, right? These 3 number of moles will now determine the pH of the solution. Will now determine the pH of the solution, right? We will use this 3 number of moles to find the pH of the solution, and that solution would be basic because the base was in excess, right? So let's see the model, how actually it really works, and that so because of what I have just mentioned, right? I said when an acid reacts now with a base, right, we need to identify the limiting reagent, because the acid and a base, they will fight each other until one of them wins, right? They fight each other until one of them wins. So we will want to find which one will get finished, will lose, which one will get finished, and which one is in excess. After finding the limiting reagent, obviously you will know which one is in excess. Now for the excess reactant, you need to know the following information. You need to know the following information, which is rare. Right. So for the excess reactant, you need to know the number of moles that reacted. You need to know the initial number of moles. Then you also need to know the excess number of moles. The aim of doing this is so that you can find out the number of moles that are in excess, so that this number of moles that are in excess will determine the pH of the solution. Just like I have demonstrated to say, if I had two number of moles for the acid, if I have got two number of moles for the acid, and I have got 5 number of moles for the base initially. Now, what is it that will happen when you react these two? Remember, you initially have 5 number of moles. This side, you initially have 2 number of moles. You initially have 2 number of moles. What is it that will happen there? Right? So this one will cancel with that. This will cancel with that. They fight each other. So these two will consume these two. Now, which ones? So two of them were reacted. So two of them were reacted number of moles. So we can see this is what the reacted number of moles now will be 2 of them. Then these were initial number of moles. Let me just write it like this. Okay, we said now these are reacted number of moles, 2 of them, and these ones were initial. Now to get the final number of moles, it will be the initial number of moles minus the reacted number of moles minus the number of moles that reacted minus the number of moles that reacted there. So this final number of moles, which are also called the excess number of moles. Remember, this final number of moles, I can also say it is the excess number of moles. It is the same thing. I will just use the same denotion, a way of representing them. I can use this, or I can use this. I mean the same thing when I say number of moles in excess, and when I say a number of moles final, I will be meaning the same thing in this case. Let's take note of that. Now let's check the number of moles that are final. This number of moles that are final, which is 3 number of moles in this case, you will have 3 number of moles in this case. So we're going to have final number of moles as what? As 3. Right? Number of moles. This 3 number of moles will be the one that will determine the pH of the solution, because we want to know what is the final pH. What is the pH of the final solution? So this part here is about the excess reactant. It's information about the excess reactant, because we have limiting reagent, then the other one will be the excess reactant. For the excess reactant, we must get the number of moles that reacted. We must know the initial number of moles, and finally we must know the number of moles that are in excess, so that this number of moles that are in excess will determine the pH of the solution. Okay, so now we know when we determine pH of the solution, is either it is the pH of a base of an acid, which we use CHOP, or is the pH of the base, which we use Cook, as indicated in previous sessions. Okay, so let's look at it. First of all, when I have this kind of reaction, we have an acid reacting with a base. Now they are saying now we must determine the pH. The question is determine the pH of the final solution. Although it's not indicated, but let me indicate it. Determine the pH of the final solution. The pH of the final solution in beaker what? In beaker C. In beaker C. So now we want the pH. This is beaker A. We pour this is beaker B, we pour them together into beaker C. Then this is where they will fight in. They will fight, an acid and a base will fight inside here. Inside this beaker, they will fight, an acid and a base will fight in here until one of them wins. And the one that wins, those number of moles will determine the pH of the solution. They will be able to give you the pH of the solution. So let's do it. What is it that is needed? We need the number of moles first. We need to know the number of moles, right? So for an acid, for our base, this is what we are given, and then for our acid, this is what we are given. Let's get the number of moles of each first. So we say concentration is equals to number of moles divided by volume. Let me start with our base. Let's see. Right, so for our acid, this is for our acid. So start with this. The concentration here, the concentration is 0.14 is equals to number of moles, and the volume is 0.35 moles. Then the number of moles now will be equals to, right, so we got this number of moles for NaOH. Now let's go and find the number of moles for an acid. It will be C is equals to number of moles divided by volume. Right? Then the concentration is 0.27. 0.27. Right, so we substitute there. So then N is equals to, so we get this number of moles there. Right, so right now let's look at, after having the number of moles for each, so let's check what is the next step. Right, if you have now this number of moles, these are, now what do? We now want to determine the limiting reagent. So my easiest way of identifying a limiting reagent, I just come and look at the coefficients here, coefficients here, coefficients there. So I'm going to divide this number here. I'm going to divide this by the coefficient, which is 1, and the coefficient here, which is 1. The coefficient of this is 1, so I divide this by 1. The coefficient of the base of the acid is 1, so I divide by 1 there. That's what I will do. That's my easiest way of identifying the limiting reagent. Right, so let's divide. So I divide here by 1, this number of moles by 1. I also divide this number of moles by 1, and I still get the same. Right, still get the same. Now what is it that now happens is that I look at which one is bigger now. The one that is big is excess, and the one that is small is limiting, right? The one that is less is limiting. So I can see that this number of moles are less. Okay, this number of moles are less compared to this number of moles. compared to this number of moles, these ones are less number of moles. So because they are less, this is a limiting reagent. This is limiting reagent. Limiting. This is going to be our limiting reagent, which is NaOH is our limiting reagent. It's going to be our limiting reagent. Okay, NaOH is going to be our limiting reagent. Now, remember that I said you are using this procedure that I've indicated. I said we are using limiting RIRE. Okay. Now, so we have identified the limiting reagent. Now, this part is about the excess reactant. It's information of excess reactant. What do we do? For the excess reactant, we must know the reacted number of moles. These are an initial number of moles. These are still reacted number of moles. Then we also use the excess number of moles. So what are we going to do? We're going to say, write this number of moles. We calculate them. We're going to calculate this number of moles. Then for this part here, I'm saying the initial number of moles is equals to the reacted number of moles plus the excess number of moles. Now, I already have initial. I would have calculated the reacted. So I would want to know what is the excess number of moles there. Right? That is the procedure that I'm trying to follow. Let's see. So let's calculate the reacted number of moles for the excess reactant. For the excess reactant. So we are going to determine that using ratio. We use ratio. We're going to say HBr. HBr is to NaOH. The ratio is 1 is to 1. Now, we know that all the number of moles for the limiting reagent will get consumed, but it will be consumed by how many moles from this side? Because these ones here, not all of them will react, because this is the excess reactant, right? According to what we have identified, according to how we identified, right? So not all this number of moles will react. Some part of it will react. So this part of them will react with this number of moles completely. Okay, we'll cancel these ones completely. Okay, so now 0 point, we say now this 0.049 moles will be cancelled by how many moles for the excess. We want to know the number of moles for the excess using ratio. Okay, then we cross multiply. You can cross multiply. You multiply this, multiply that, or you can say 1:1 means they are the same. The answer would be the same. So the reacted number of moles for the excess is equals to 0.049 mole of HBr in this case. Okay, so this number of moles for HBr, are the reacted number of moles. These ones are the initial number of moles for the what? For the HBr. Okay. Now we now say, okay, we said for the, so let me just do this. We are saying for the excess we are following this rare. Okay, we already calculated using ratio, we calculated the number of moles that reacted. Then I'm going to use this part to say initial number of moles is equals to the reacted plus the what? The excess, so that I can get what the excess is, because I've got initial number of moles, I've got the reacted number of moles. This R and this R are the same. They are the same. It's just for procedure. Okay, so now so what are we going to say? We're going to say now, following that, we're saying the initial number of moles is equals to the number of moles that reacted plus the number of moles that are in excess. If I don't write E, I can also write F. Still the same thing. I can still write F final. So E and final is the same thing. I use them interchangeably because okay. Now, for the excess reactant, the initial number of moles, these were the initial number of moles. This one's here. Sorry, this one's here. They were in the initial. This one's here. So say 0.1215 is equals to the reacted. These are the reacted number of moles for the excess. 0.049 plus number of moles that are in excess. What is the answer to that? So number of moles that are in excess is equals to 0.125 minus 0.049. And that will give us 0.0725 moles of HBr. So we can see that HBr has got 3 number of moles. We already have 3, it has got 3 number of moles. We have got this number of moles that are initial. We have got this number of moles that are reacted, and we've got this number of moles that are what? That are in excess. So it is initial, reacted, and the ones that are in excess. So we managed to do that. Right. Now, I said after the word rare, there is the word chop or cook. But in this case, we are going to use chop. The reason we use chop is because we are calculating the pH of a base, of an acid. Why? Because the acid is the one that is in excess. So we are calculating the pH of an acid because it's the one that is in excess, which is HBr. So we are going to follow the chop method. With the chop method, we want to find what the concentration is. We want to find the concentration. Right. We want to find the concentration. So we're going to say now, concentration is equals to number of moles over volume, because we don't have the concentration, right? Now, the number of moles, this concentration, this number of moles are the number of moles that are in excess. And this volume should be the total volume, the combined total volume for the two. When you combine the volume of the two, the acid and the base, this will be the total. Okay, so just check. So we can see what were the volumes, what the volumes were. So the volume of the acid, the volume here was this one, and the volume was this one. There. You're combining the two volumes together to form, because you have mixed them together. So the volume, the total volume inside here, because what is happening inside here is that we have got the excess number of moles and the total volume that is remaining inside is bigger. Okay, so we add the two. So we the total volume now, it's the 0.14 plus the 0.145, which is 0.59. That is the volume. Right. That is the volume that we're going to use. There. So the excess number of moles that we got were 0.0725 divided by 0.59. So we get concentration. So that we get the concentration there. So this is the this is the concentration that we get. You don't round off, okay? You don't round off. You're going to put this into, or you can just simply write it in scientific notation. Right. So this is the concentration. Now to find the pH. So before that, we now say, okay, we now have to find the concentration of hydronium ions. And the concentration of the hydronium ion will be the ratio. You find the ratio. You now find the ratio. Say HBr is to hydronium ions. What is the ratio? 1:1. Meaning the concentration now will be the same. The concentration of hydronium ions there. So the reason we say the ratio between the two is 1:1 is because I asked myself how many H's are there in this one HBr. So one HBr has got one H. So the ratio is 1:1. Remember, H is the hydrogen ions, which has got the same concentration as the hydronium ions. Okay, right. Now, if we cross multiply, we will get this as the concentration of hydronium ion. Now the pH is equals to negative log concentration of hydronium ion. Negative log concentration of hydronium ions. Use square brackets. And this is equals to negative log then I substitute the concentration 0.12288 35593, and this will be equals to 0.91, and that is the pH of the solution. That is the pH of the solution there. Right, so let's look at another pH solution, another pH calculation. We want to calculate the pH of the final solution. The aim is to calculate the pH of the final solution here. C. Okay, so you're given beaker A and beaker B. They pour them into beaker C. Then we want to calculate the pH. Now, what will happen? We know that we have to determine the limiting reagent, but we must use number of moles to determine that. So let's see. For this one, I'm going to say the number of moles. What is the concentration? Concentration is equals to number of moles over volume. The aim is to calculate the number of moles first. Now the concentration of A, the acid, is 0.2. Is equals to number of moles over the volume is 0.4. 0.4 volume. Right. If we multiply them, what do we get? So N is equals to 0.08 mole. Okay, of HCl. Then for this now, say concentration is equal to number of moles divided by volume. The concentration is 0.45. Is equals to number of moles, and the volume is 0.45. Let's check the right, sorry, the volume is 0.5. Pardon me, 0.5. So the number of moles is equals to, if we check there, we get 0.225 number of moles. Right, so then we divide now. We want to find the limiting reagent. After getting number of moles, you go and find the limiting reagent. The limiting reagent you divide by the coefficient. So the coefficient of this one, this is 2, sorry. The coefficient of HCl is 2. The coefficient of barium is 1. So you've got 1 there. You've got 2 there. You've got that 2 there. And you have 1 there. So now this number of moles here, these ones I divide by 1, these ones I must divide by 2. Divide by 2 there, divide by 1 there. So you get 0, it says 0.08 divided by 2. It's 0.04. And we say 0.225 divided by 1, you still get the same answer. Right, I look at the smallest. The small one is this. This is the small one. Okay, so this is the limiting reagent because it is less. So meaning now HCl, the acid, is there. Then automatically the base will be in excess. So we say barium hydroxide is therefore in what? In excess. Okay. Since when we divide, after dividing by coefficient, the one that is less is the limiting reagent. The less is the limiting reagent. Okay. So now I'm going to do what? I'm going to use now rare. I'm going to use rare. Right. Rare. So if I use rare is about the excess reactant. It's an information about the excess what? Reactant. Which is in this case about this. Meaning you have to find now the reacted number of moles of HBr. The initial number of moles must be known so that you can get the excess number of moles. Okay. And I said this part is just guiding you the formula. I said initial is equals to reacted plus excess. So now we're going to get the reacted number of moles using ratio. We're going to use ratio to do that. The reacted moles of what? Of HBr. So we say this is HCl. Is to barium hydroxide. The ratio here is 2:1. Remember, I'm looking for the number of moles of the excess that reacted with all the number of moles of the HBr, of the hydrochloric acid. So I write 0.08. So we use 0.8 because this is the number that we use. We use this one. Okay. Right, we don't use the one that we divided by coefficient. We don't use that one. We use the original number of moles that we got, the first number of moles that we got for HCl. is the ones that we use. Okay, those ones where you have divided by coefficient, they are used to identify the limiting reagent. Now you cross multiply and you'll get 2 nr is equals to 0,08. Then you'll divide both sides. You divide by 2. You divide by 2. So n is equals to 0.04 mole. Of barium hydroxide. So this number of moles that we just got here, we have initial number of moles for the excess. For the excess reactant, we have initial number of moles, which is this. These are the initial number of moles. We also have the reacted number of moles, which are these ones that we just got here, this number of moles. Those are the reacted number of moles. Okay, now after getting this, we must get the excess number of moles. We must get the excess number of moles. So this is what we get. We say from the right, now this part here, we got the reacted number of moles. So then I say the initial number of moles is equal to the reacted plus the ones that are in excess. So according to the formula, this is the formula. So we can get the number of moles that are in excess. So the number of moles that are in excess, okay, the excess number of moles is equal to 0.185 mole. Of barium hydroxide. So we can check for barium, we've got initial, we've got reacted, and now we have what? The excess. Initial, reacted, the excess. The two R's are the same. Okay, it's talking about the same thing. All right, now after getting the excess, we must get the volume. Sorry, we must know the concentration, because after this weight come, we have got the weight chop or the weight cook. But in this case, we're going to use cook because we are talking about the base. The base is the one that is in excess. So we're determining the pH of a base. So we use cook. Okay. Now, so let's get to concentration. Concentration is equal to number of moles divided by volume. And this volume must be a total volume. And this number of moles must be number of moles in excess. So 0.18 185 divided by the volume. Let me check the volumes. Zero comma 5. This is the volume of 0.5, 0.5 volume, and 0.4 volume. Okay. So 0, 0.5 plus 0, 0.9. That is our total volume. So now the concentration is equals to 0.20 55555, just like that. Yeah, 5555. Yeah. Then mole per cubic decimeter. Right, so now this is the concentration. After getting the concentration, where do we go? We come here. Concentration of OH. Right, we now want the concentration of OH because we have got the concentration of the base. Right, if we check now, the ratio of the is to OH. Okay, what is the ratio? The barium has got 2 OH. So this is 2 is to 1. And the concentration was 0.205 recurring. Just like that, 5555555. You continue writing it. It's just that here I don't have space. Then concentration of hydroxide. You're going to cross multiply here. You're going to cross multiply. Sorry, the ratio here is not correct. We say in one is a base, we have got 2 hydroxide ions. So it's 1 is to 2. Okay, so on the base, it must always, on the base must always be 1. Then is 2, check the hydroxide, whatever hydroxide ions are. Okay, you cross multiply. So for the concentration of OH minus, it is equals to 2 being multiplied by 0.205555556, just like that, mole per cubic decimeter. Right, mole per cubic decimeter. Right, so now let's check. And if you multiply here, you get 0.411111. So what do you get there? The concentration is 0.411111, just like that, mole per cubic decimeter. That is the concentration of hydroxide ions. Now I calculate I use KW. Now I have to use KW formula. So in the next slide, it will do that. So said we are using Cook, and now we want to use KW. Say KW. KW is equals to the concentration of hydronium ions multiplied by the concentration of OH minus. is equals to 10 to the power negative what? This is equals to the concentration of hydronium ions 0.4111. So now the concentration of hydroxide ions, not of hydroxide ions, of hydronium ions is equals to 2.43 times 10 to the power negative 14 mole per cubic centimeter. Now I can come to the pH. Say pH is equals to negative log concentration of hydronium ions. Negative log then this is 13.61. Here's the pH of the solution, the pH of the final solution.